My name is Martin Springer. I'm at the National Renewable Energy Laboratory in the United States. And today I'm going to talk a little bit about gas breakage in photovoltaic modules. This is taken from a news article published in The Economist about 2 months ago. And they put in a really interesting graph here on the right-hand side. So everything here in yellow was predictions on how much solar photovoltaics we are going to put out or install every year. And this is in gigawatts. And the black line here is what actually happened in reality. So this means that photovoltaic technology has outperformed all of the forecasts that we had over the last 10 to 15 years here. And we've reached a point where we are installing more solar panels every year than we ever had in human history before. And we had to change a couple of things to get there. One thing, of course, we need to make those modules cheaper to make them economical. And to achieve this, a lot of technological changes have happened more or less just in the last 10 years. So a module that we deployed like 2014 is shown here. So if I talk about photovoltaics, I do mean those crystalline silicon cells that can convert light directly into electricity. Those cells are brittle. They need to be protected from the environment. They need to be electrically insulated. And so we package them with polymer materials. Then we put some gas on top of it. And then we put a frame around it so we can handle them. And over the years, we've made a couple of changes in this design. We've changed the materials. We've changed the manufacturing processes. And we've made those modules much larger, as I'm going to show on the next slide. And all of those changes have helped to actually increase the power output. So we do need to put less modules out to actually achieve the same power output. And I want to focus just on a couple of aspects here that we've changed. So I'm a reliability engineer. And so we look at the lifetimes of those modules. And so we want to predict or say what's going on if we put those huge modules out in the field over like, let's say, 20, 25 years or even longer. And so here, this is an evolution that happened over the last 10 years. So those modules got really big. They're about 2.5 meters high now. You can see here Jim and Craig lifting them. And there were a couple of improvements also in cell technology that enabled that. On the same hand, we also made modules floppier. What do I mean by this? So there's a new cell technology that does allow the conversion of light into electricity from the front and the back side. And so previously we had like polymer back sheets here on the back, which were usually white, so no light could come to the cells. But if you want to take advantage of bifacial cells, we had to put a transparent back sheet on the back. And the cheapest one is glass. But glass is heavy. And so what people did was to reduce the glass thickness on the front and the back in this packaging. On the same hand, so the glass got thinner. And if you're familiar with glass heat treatment, you know that it's getting really difficult to heat strengthen or temper it if the glass is getting thin. And I'll talk about this a little later. And similarly, to cut costs, we also decreased the frame sizes. This was like more common like 10 years ago, and now those aluminum frames are getting smaller and smaller because aluminum is expensive. And you can already see where I'm going with this. Additionally, we've made changes to the model, but we've also made changes to the system. And so 10, 15 years ago, usually people build like a nice substructure where the module could really hold on to. But building a steel substructure is really expensive. And so it's easier to actually have the module carry some of the loads to make it cheaper. And the most common installation method here is now a tracker-mounted system that actually allows to track the sun and to maximize the energy output. But what you can see here, what I'm trying to indicate here is like the clamping positions of those modules. And we try to amplify the deformation figures of those modules. And so you can expect, if those mounting points are getting smaller and smaller, you get stress rises here, and this might actually cause some issues in this module. And so from a reliability standpoint, it's great that we're putting out so much, just from an energy transition perspective, it's great that we're putting out so much new solar technology. But from a reliability perspective, this is almost like a nightmare scenario. We're building all those new modules with technology that hasn't been proven yet. And we want to make sure, though, that those modules actually survive 25, 30 years in the field. To enable this, all those changes. We do have qualification tests, but what people did was they derated the test and design loads. So 10 years ago, this was the standard. So usually a module has to pass a static mechanical load test. You apply pressure on top. This was like 5,400 Pascal under certain conditions. And nowadays people say, oh, this is too high. We don't have so much snow anymore. We don't have that high wind loads. For tracker mounted system, you can derate those. And in certain locations of the Earth, this might be right, but not in all of them, and definitely not in all where we're deploying it. And you can already guess this is causing issues. And we got aware of those glass breakage issues late 2023, 2024, and the first articles came out that glass breakage is a growing phenomenon in large-scale PV systems. Since then, a couple of other articles have been published, and you can see here the failure mode, that the glass is spontaneously breaking in the field. This was for really new systems, like not even a year old. There was no severe weather event. There was no storm coming through, no hail event, nothing. Those modules were installed, and some of the sites weren't even commissioned yet. So our task was then to figure out what's going on. And we do have what's called qualification testing, which is specified in the standard here. And there is one sequence in there that looks at static mechanical load testing. But it only tests up to a certain test load that I've showed you before. And this test load got smaller and smaller and smaller over the years. And so if you look at the actual load, let's say this is wind or snow, then you usually end up with some kind of distribution, and you can derive a design load for a certain site at a certain location around the world. And then we test up to the test load, and if the module succeeds this test, then we can get the normative safety factor. However, this qualification test does not look at a fracture load, for example. So we're not testing to failure. So we never actually know how high the actual safety margin was. So one thing we were thinking, maybe we've just overbuilt those modules in the past, and now we've actually, with all those design changes, we've pushed this strength distribution down, and maybe we've pushed it down a little bit too far. And so the first thing we wanted to figure out is, okay, how does this actual strength distribution for modules look like? So we came up with the study design here, and we did some initial feasibility results where we built like the static mechanical load test setup. This black bar here is the PV module. We apply uniform load. It's mounted on the actual mounting positions, and we put a high-speed camera on top. So the idea was to figure out, okay, what is the fracture load? And we also wanted to figure out where is the glass breaking from. And so those are images from the high-speed camera, and you can see, okay, crack initiation started here. You can actually see the crack front here with the fracture pattern. And then this is the completely damaged module. And so the idea was we have a testing campaign of like 30 or more modules to get this fracture distribution, and then include this in our What's Cracking app. And this is a COMSOL finite element application. This is actually a pretty nice application builder that COMSOL has here, which allows you to put in a finite element model and actually distribute it to partners outside that don't have a license for COMSOL. And then you can specify what parameters they can vary. And so, and then you can do like some simple analysis like shown here. This is like the fracture probability of the cells. And you can see here, there's like, if the loading points are really far out, then the fracture probability is low for most of the cells. But as I mentioned, now we've decreased those mounting points, and then the fracture probability starts. So the idea was conduct this testing, conduct this study on glass breakage, and then also add this here into this finite element app based on Weibull analysis and weakest link theory. This was our idea, and this is when I put in the abstract for this conference, and this is why I'm in the computational mechanics section. However, once we started testing, this is how the actual test setup looks like, and you can see you can get large deflections of those modules before you actually get glass breakage. At some point you can break it though, and I hope you can see it. There's like some glass breakage going on here in this module, and you get the scattered effect here if you do this uniform mechanical loading test. However, if we do compare this to field failure, and this is probably really hard to see, but there's only a single crack here. I tried to highlight this with the arrows here, versus this is what we're getting in the static load test. So our test setup doesn't really capture what's going on in the field. So we had to reassess our study and to figure out what's actually going on in the field out there. And one issue that we came across is the thermally strengthening of the glass. especially since it's so thin. Most of the standards actually only specify the heat treatment for thicknesses above 3 millimeters. And then you usually can differentiate between tempered glass and heat strengthened glass. And tempered glass usually fractures in like a lot of small pieces, versus heat strengthened glass is more like a fracture characteristic similar to annealed glass. And the issue with thin glass is that it's getting really hard to introduce those residual stresses, because it's getting difficult to just cool the outer surface of the glass, while here the neutral axis is still hot to introduce a stress state. And so we were wondering, okay, so maybe there are like different modules, one that has like tempered glass and one that has only heat strengthened glass. And so you can use a scatter-like polariscope to actually figure out what is the residual stress state in the glass. But once we measured them, both of those modules seem to be fully tempered, based at least on those compressive stress measurements that we did. And so we weren't completely sure what's going on. So how can we actually crack like tempered glass with a single crack? This seemed a little weird to us. However, if we experimented a little more with it, we have here an unloaded PV module. And on the back here, those are so-called junction boxes where the cables are coming out. And so we removed one of those and just put like a big notch into it, like with the file that's shown here. And then we got like the spiral forming crack. And remember, this is like in a glass that has a compressive stress similar to tempered glass, where you would actually expect it to shatter in a lot of pieces. Whereas here we just get like a one single crack. And so this is where we're at currently. So what we think is happening in the field is that there's an interaction between the aluminum frame and the glass laminate. And you can see we removed the aluminum frame here for one, and it can happen that there's sand in there. And so with wind vibrations of those mounted modules, we do expect that there might be some scratching going on the glass surface between the aluminum frame and the glass, which introduces then scratches and voids, which might cause then cracks to propagate similar to this. However, we also see cracks like that, where you have like a circular shape just in the glass, which doesn't touch the edges at all. And so we don't have an explanation for that yet. So if anybody here knows, okay, what might be going on here, I'm really happy to hear about that. Thank you very much.